The diamond shield, the material that makes the dome real. Part 3 of the hypersonic gap. The strategic framework of continental defense rests on an unyielding law of attrition. For 7 decades, every architecture built to intercept incoming missiles has operated on the wrong side of a brutal economic curve. We build a multi-million-dollar interceptor to destroy a threat that costs a fraction of that amount to manufacture and launch. In the context of a modern massed theater engagement, this structural imbalance is fatal. According to data compiled by the Congressional Budget Office, the life cycle cost to deploy and sustain a comprehensive, multi-layered homeland missile defense shield, the conceptual Golden Dome, is projected to climb between $542 billion and $1.75 trillion. To justify an investment of this magnitude, the system must do what no defense grid in human history has ever accomplished. It must invert the cost-exchange ratio. It must make the marginal cost of a single intercept cheaper than the weapon it destroys. This economic inversion is the foundational promise of the directed energy layer. When a solid-state or chemical laser system neutralizes an incoming threat, the cost per shot is no longer measured by the manufacturing price of a rocket motor, a guidance package, and an explosive warhead. Instead, the marginal cost of an intercept is driven down to the price of the diesel or electricity required to generate the beam. A target is tracked, an aperture dwells, and a high-energy stream of photons deposits catastrophic thermal energy onto a hull for pennies on the dollar. On paper, this economic logic is flawless. It represents the only mathematically viable mechanism to blunt a saturation attack without bankrupting the defending nation. But this entire construct contains a hidden systemic flaw. The economic calculation assumes the weapon can fire repeatedly, shot after shot, without suffering structural degradation. It assumes the delivery mechanism, the physical optical assembly that shapes, focuses, and projects the beam, is a static component. In reality, the optics are a consumable asset. At high average power, the physical lenses and windows that transmit the laser beam absorb a minute fraction of the energy passing through them. Under intense, continuous wave operation, this fractional absorption transforms the optic into a thermal heat sink. The lens expands, distorts, and ultimately fractures. If an optical window must be replaced after every engagement cycle, the cost of the intercept is not the price of the electricity. The true cost is the price of a precision-engineered, large-aperture optical element, coupled with the systemic downtime required to swap the component in the field. Without a radical departure in materials science, the directed energy layer remains an expensive, fragile laboratory demonstration. The economic argument for the Golden Dome collapses because the thermal optics bottleneck renders sustained, high-power defensive operations physically impossible. This flaw is not new to the defense establishment. Every prior generation of missile defense has collided with the same attrition math. The Sprint and Spartan interceptors of the 1970s safeguard system were estimated to cost millions per round even in the dollars of that era. The Patriot PAC-3 MSE kinetic round runs roughly $4 million per missile, and doctrine calls for firing 2 against a single inbound to reach an acceptable probability of kill. A Standard Missile 3 from the Aegis system costs upward of $12 million per interceptor. Against a threat manufactured for $3 to $5 million, the defender spends 2 to 4 times the attacker's cost on every engagement, and the attacker can always manufacture more rounds than the defender can stockpile interceptors. A saturation salvo is therefore not a tactic of desperation. It is the mathematical inevitability of an unfavorable cost curve. The directed energy layer is the only layer in the architecture that escapes this law because its projectile is photons and its fuel is electricity. But the escape holds only if the weapon fires more than once. The moment the optic becomes a consumable, the directed energy layer inherits the same attrition arithmetic that doomed every kinetic defense before it, and the economic case for the trillion-dollar dome dissolves into the price of replacing precision optics after every shot. Act 2. The thermal wall. To understand why directed energy hits a hard engineering wall, one must examine the behavior of conventional optical materials under extreme thermal load. In standard industrial and low-power military laser systems, windows and lenses are typically fabricated from materials like zinc selenide, fused silica, or optical-grade glass, while reflective paths rely on copper mirrors. For systems operating in the tens of kilowatts, these materials are perfectly adequate. They possess acceptable transmission windows and manageable absorption coefficients. However, as a laser system is scaled to meet the requirements of continental defense, the physics of conventional materials change catastrophically. The primary metric governing this failure is the continuous wave laser-induced damage threshold. For premium optical-grade zinc selenide, the bulk absorption index at key infrared wavelengths sits between 5 × 10 to the -4th and 1 × 10 to the -3rd per centimeter. This means that for every megawatt of laser power passing through a 10 mm thick window, between 50 and 100 watts of pure thermal energy are absorbed directly into the crystalline lattice of the material. As this heat accumulates, it triggers a phenomenon known as thermal lensing. Zinc selenide has a positive thermo-optic coefficient, meaning its index of refraction changes as its temperature rises. Because a high-energy laser beam has a Gaussian or non-uniform intensity profile, the center of the optical window becomes significantly hotter than its edges. This uneven temperature distribution creates a localized gradient in the refractive index. The flat window inadvertently transforms into a powerful, unpredictable lens. The consequences of thermal lensing are immediate and destructive. The wavefront of the laser beam is warped, causing the beam quality to collapse. Instead of a tightly focused, coherent spot capable of burning through a target at long range, the beam aberrates, spreading its energy over a wide area and rendering the weapon ineffective. If the power is pushed higher, the material reaches its structural limit. Zinc selenide possesses a relatively high coefficient of thermal expansion, roughly 7.57 × 10 to the -6th per degree Celsius, combined with a low Knoop hardness of just 120 kilograms per square millimeter. The rapid, uneven thermal expansion generates massive internal mechanical stress. When the local power density exceeds the material's threshold, typically failing at a few kilowatts per square centimeter under sustained flux, the optic undergoes catastrophic thermal fracture. The window cracks, scatters the laser energy internally, and instantly destroys the weapon system from the inside out. This thermal wall represents a rigid boundary. Using conventional optics, scaling a directed energy weapon past roughly 50 kilowatts guarantees the self-destruction of the aperture. The copper mirror alternative fails along a parallel path. Copper carries heat well, but it is a metal, and under the flux of a high-energy beam, its reflective surface distorts through thermal expansion and figure error long before it fractures. The beam that should reflect cleanly off the copper instead scatters, and the weapon loses coherence at the very first optic in the train. Fused silica, the workhorse of lower power systems, suffers the same thermal lensing failure as zinc selenide once the average power climbs past the regime where a drone can be killed at close range. Every conventional optical material shares the same fatal architecture. It must both transmit the beam and survive the heat it absorbs, and no conventional material can do the second job at the power the first requires. The 50 kilowatt ceiling is therefore not a procurement target. It is a thermodynamic wall, as rigid as the sound barrier was to aeronautics, and every attempt to push a conventional optic laser past it has ended the same way. The aperture destroys itself before it destroys the target. The directed energy layer cannot be scaled to the megawatt regime that a hypersonic engagement demands by incrementally improving zinc selenide or copper. It requires a material that does not exist anywhere on the conventional optics menu. Act 3. The diamond ceiling. Overcoming this barrier requires a material that possesses an impossible combination of physical properties: an ultra-low absorption coefficient, a near-zero thermo-optic distortion index, immense mechanical hardness, and a thermal conductivity that exceeds that of the finest metallic conductors. There is only one material in the known universe that meets these criteria. It is synthetic diamond. For centuries, diamond was viewed exclusively as a geological rarity and a gemstone. Today, in the realm of advanced defense engineering, it is recognized as the ultimate optical crystal. The foundational metric that sets synthetic diamond apart from every other optical material is its staggering thermal conductivity. At room temperature, high-purity chemical vapor deposition diamond exhibits a thermal conductivity of approximately 2200 watts per meter Kelvin. To put this value into perspective, copper, the industrial gold standard for thermal management, possesses a thermal conductivity of roughly 400 watts per meter Kelvin. Synthetic diamond moves heat more than 5 times faster than copper, and it does so while being a completely transparent, electrically insulating dielectric. In comparison, zinc selenide thermal conductivity is a meager 18 watts per meter Kelvin. Diamond is over 100 times more efficient at conducting heat away from a thermal load than the very material it is designed to replace. This unparalleled heat transfer capability is paired with extreme optical and mechanical robustness. Diamond possesses a Knoop hardness of approximately 10,000 kilograms per square millimeter, making it the hardest known bulk material. This immense structural rigidity gives it an exceptionally high resistance to thermal shock. Its coefficient of thermal expansion is a mere 1.0 times 10 to the -6th per degree Celsius, meaning that even when subjected to extreme temperature swings, its physical dimensions remain virtually unchanged. Furthermore, synthetic diamond possesses a vast optical transmission band, stretching from the deep ultraviolet all the way into the far infrared, covering the exact near-infrared and mid-infrared wavelengths utilized by high-power solid-state military lasers. The realization of diamond as a viable engineering component is driven by advances in chemical vapor deposition synthesis. Rather than relying on the random, flawed structures of natural diamonds or the crushed output of high-pressure, high-temperature industrial presses, chemical vapor deposition allows technicians to grow large, high-purity crystalline structures atom by atom. Inside a vacuum chamber, a plasma of methane and hydrogen gas is ignited via microwave energy. Carbon atoms dissociate from the gas and settle onto a substrate, meticulously building a flawless, isotropic polycrystalline or single-crystal diamond lattice. By controlling the purity of the precursor gases and the temperature of the growth phase, engineers can fabricate freestanding optical elements whose thermal and optical performance directly approaches that of a theoretically perfect crystal. The path to optical-grade diamond is short in history, but long in difficulty. The first synthetic stones were grown by General Electric in 1954 under extreme pressure and temperature, the high-pressure, high-temperature method that still dominates abrasive and industrial-grade production. That process yields the crushed, polycrystalline grit used in cutting tools and drill bits, not the flawless windows a laser requires. The breakthrough came with chemical vapor deposition, refined through the 1980s and 90s, and commercialized by firms like Element 6, a De Beers industrial subsidiary, and a growing field of defense-oriented CVD specialists. Only CVD can grow the large, freestanding isotropic crystals an optical train demands, and only CVD can control the purity down to the parts per trillion nitrogen and boron contamination that would otherwise turn a transparent window into an absorbing one. The defense industrial base now recognizes that whoever scales CVD diamond to the diameter and growth rate an aperture requires owns the directed energy era, in the same way that whoever scaled aluminum smelting owned the aircraft era, whoever mastered uranium enrichment owned the nuclear era, and whoever mastered photolithography owned the semiconductor era. The race is not for the laser. The race is for the diamond that lets the laser survive itself. Act 4. Diamond in the beam path. Integrating chemical vapor deposition. Diamond into the optical train of a directed energy weapon fundamentally alters the physics of the system. The material is deployed at 3 critical nodes within the beam path, with each deployment resolving a specific thermodynamic bottleneck that previously prevented the scaling of average laser power. The first and most visible application is the exit window. The exit window is the final physical barrier between the controlled environment inside the laser weapon and the external atmosphere. It must withstand the full, unmitigated flux of the output beam while resisting environmental degradation like sand erosion, salt spray, and atmospheric pressure differentials. When a zinc selenide window is exposed to a multi-hundred kilowatt beam, the localized heat cannot escape, leading to the thermal lensing and fracture cycles that destroy the optic. A diamond exit window resolves this entirely. Because its thermal conductivity is so high, any fractional energy absorbed by the diamond lattice is instantly conducted outward to the perimeter of the window, where it can be actively removed by conventional liquid cooling jackets. The temperature profile across the window remains flat, thermal lensing is suppressed, and the exit window can survive a continuous energy flux that would melt glass within milliseconds. The second critical node is the heat spreader positioned directly behind the laser gain medium. Whether the laser utilizes a solid-state slab or a disk architecture, the active crystal that generates the photons produces a massive amount of waste heat during the pumping process. If this heat is not removed from the gain medium, the crystal undergoes optical distortion, altering the wavelength and destroying beam coherence. By bonding the laser crystal directly to a chemical vapor deposition diamond heat spreader, the waste heat is instantly drawn out of the gain medium and distributed across a wide surface area. This allows the laser to be pumped at an order of magnitude higher intensity before reaching its thermal limit, shifting the baseline capability of the power source from tens of kilowatts to hundreds of kilowatts. The third, more advanced application is Raman wavelength conversion. When a high-power laser beam travels through the atmosphere, certain wavelengths are heavily absorbed or scattered by water vapor and molecular oxygen. To circumvent this, the laser can be fired into a synthetic diamond crystal engineered as a Raman cavity. Through stimulated Raman scattering, the optical phonons within the diamond lattice interact with the incoming light, shifting the laser's output to a cleaner, deeper penetrating atmospheric wavelength with minimal insertion loss. By solving the thermal issues at the window, the gain medium, and the wavelength converter, diamond optics achieve true shot-to-shot survivability. The optical train is no longer a consumable component that degrades with use. The hardware remains intact, ensuring that the marginal cost of an intercept remains anchored to the price of the electricity required to fire the beam. The engineering of each node carries its own difficulty. Bonding the diamond heat spreader to the gain medium is not a trivial assembly step. The two materials must match in coefficient of thermal expansion across the full operating temperature range, or the bond shears under power cycling and the crystal cracks. Diamond's expansion coefficient is among the lowest of any engineering material, which forces the gain medium itself toward low expansion hosts like ytterbium-doped yttrium aluminum garnet, and demands optical contact bonding rather than conventional adhesives that would themselves absorb and fail. The cooling jackets clamped to the diamond window's perimeter must be engineered so the heat extraction is radially symmetric, because any asymmetry reintroduces the thermal gradient that produces lensing, the very failure the diamond was installed to prevent. The Raman cavity diamond must survive not only the pump beam, but the converted beam at high intensity, with its own thermal load, requiring the same CVD purity as the exit window. When all three nodes are solved, the optical train becomes permanent hardware. The weapon fires, the window survives, the gain medium stays coherent, the wavelength converter holds, and the only thing consumed per shot is the fuel that generated the electricity. That is the moment the directed energy layer stops being a laboratory demonstration and becomes the economic engine of the dome. Act 5. Engagement geometry against a glide vehicle. This material breakthrough directly dictates the engagement geometry required to defeat a modern hypersonic threat. To understand the necessity of a high-power laser layer, one must analyze the physical characteristics of the target. A hypersonic glide vehicle, or a scramjet-powered cruise missile, does not fly along a predictable, high-altitude ballistic trajectory. Instead, it enters the atmosphere early and glides through the upper stratosphere at speeds between Mach 5 and Mach 15. To survive the immense aerodynamic friction of this regime, the weapon is encased in a highly engineered thermal protection system. These shields are fabricated from advanced carbon-carbon composites, silicon carbide ceramics, and ultra-high-temperature ablative materials designed to withstand continuous temperatures exceeding 1500 degrees Celsius. To defeat a target protected by a thermal shield, a defensive weapon cannot rely on a localized, low-power laser system. Fielded laser systems, such as the United States Navy's Helios, the Army's Indirect Fire Protection Capability high-energy laser, or the Israeli Iron Beam, operate primarily in the 30 to 100 kilowatt class. These systems are highly effective drone killers, optimized to counter small, unarmored quadcopters, mortar rounds, and low-speed cruise missiles at close ranges. However, against a hypersonic glide vehicle traveling at 3 kilometers per second, a 100 kilowatt laser is entirely inadequate. At that speed, the target traverses the weapon's maximum engagement zone in a matter of seconds. To burn through a thick, ablative carbon composite hull at a distance of hundreds of kilometers, the defensive aperture must project a beam operating in the multi-hundred kilowatt to megawatt regime. The laser must deliver an immense, concentrated power density onto a single spot of the hull, overwhelming the target's thermal protection system through pure, rapid heat deposition until the structural integrity of the airframe fails. Achieving this level of power transmission requires navigating the honest constraints of atmospheric propagation. Even with flawless diamond optics, the laser beam must still traverse miles of turbulent air. This journey introduces the phenomenon of thermal blooming. As the high-energy beam propagates through the atmosphere, the air itself absorbs a small fraction of the laser energy. This warmed air expands, decreases in density, and acts as a negative lens, causing the beam to defocus and spread out before it reaches the target. This effect is exacerbated by atmospheric turbulence, crosswinds, and suspended particulate matter like dust or humidity. To mitigate thermal blooming and maximize energy delivery, the engagement geometry must be precisely optimized. This is where the boost phase and early glide engagement windows become strategically vital. When a hypersonic weapon is in its boost phase, climbing rapidly through the denser layers of the atmosphere, or when it enters its early glide phase in the near vacuum of the upper stratosphere, the atmospheric density is significantly lower. By locating the directed energy interceptor layers at high-altitude stations, on forward-deployed maritime platforms, or via orbital configurations, the beam path passes through a much thinner atmospheric column. This geometric advantage dramatically reduces thermal blooming and turbulence, allowing a megawatt-class laser equipped with diamond exit windows to maintain a tight, lethal dwell spot on the hypersonic vehicle before it can execute evasive maneuvering in the lower atmosphere. The dwell time arithmetic against a hardened hypersonic hull is unforgiving. A fielded 100 kilowatt system can burn through the thin skin of a quadcopter in roughly 2 to 3 seconds at close range. A carbon-carbon thermal protection system engineered to survive 1500 degrees Celsius of sustained aerothermal heating demands orders of magnitude more deposited energy before the underlying structure fails. At megawatt class, the dwell time against a hypersonic hull at hundreds of kilometers compresses into a few seconds of continuous burn, which is precisely the window in which the geometry must be held. This is why the adaptive optics layer matters as much as the diamond. Atmospheric turbulence warps the beam on millisecond timescales, and a deformable mirror upstream of the diamond exit window must pre-correct the wavefront continuously, reading the turbulence and reshaping the beam faster than the air can distort it. Without the adaptive optic, the diamond window survives, but the beam still scatters before it reaches the target. With both, the megawatt beam holds its spot on a 3 km/s target long enough to defeat the hull. The engagement is a closed loop. The tracking layer feeds the pointing, the adaptive optic pre-corrects the air, the diamond window survives the flux, and the gain medium sustains the power. Break any link, and the shot fails. Hold all of them, and the glide vehicle dies before it maneuvers. Act 6. The enabler, not the whole shield. Yet, an objective evaluation of this architecture demands that we view synthetic diamond as an enabler, not as a complete standalone shield. While diamond successfully resolves the internal thermal management bottleneck of the laser weapon itself, it does not rewrite the laws of physics governing atmospheric propagation or eliminate the steep industrial and logistical challenges of the supply chain. The process of growing optical-grade synthetic diamond is exceptionally slow and capital-intensive. While industrial-grade diamond film can be deposited quickly for cutting tools, growing a thick, freestanding single-crystal or high-purity polycrystalline wafer suitable for a large aperture laser window is a painstaking process. Growth rates within a chemical vapor deposition chamber are measured in microns per hour. Producing a single optical window with a thickness of several millimeters requires weeks of continuous, uninterrupted plasma deposition under precisely controlled temperature and pressure vectors. Furthermore, there is a strict physical limit to the size of these optics. To date, the largest single crystal diamond optics successfully grown in laboratory environments are limited to dimensions of roughly 20 to 30 millimeters square. For the massive apertures required by megawatt-class weapon systems, which often require windows spanning 10 to 20 centimeters or more in diameter, engineers must rely on polycrystalline diamond configurations. While polycrystalline diamond can be grown in larger diameters, up to roughly 140 millimeters, the boundaries between the individual crystal grains introduce minute optical scatter and residual internal stress. These imperfections can cause subtle beam distortion at extreme power densities, requiring complex real-time adaptive optic systems to correct the wavefront before it exits the weapon. Because of these manufacturing bottlenecks, megawatt-class fielded laser systems remain firmly in the developmental and experimental stages, rather than being operational, off-the-shelf defense assets. The industrial base required to mass-produce optical-grade diamond components at scale does not yet exist. A continental defense strategy cannot rely on a handful of boutique, laboratory-grown lenses to secure an entire airspace. This industrial gap is colliding with a rapidly accelerating threat matrix. Intelligence assessments indicate that the combined hypersonic inventories of near-peer adversaries are on a trajectory to triple, expanding toward an estimated 5,000 deployed weapons by the year 2035. This massive inventory represents a capacity that can easily saturate any defensive grid reliant solely on traditional, kinetic interceptor missiles. The strategic synthesis is therefore absolute. The concept of the diamond ceiling is not a poetic metaphor for an unbreakable defense. It is a literal description of an upstream material science requirement that dictates the viability of global security architecture. Without the mastery of grown diamond optics, the multi-trillion-dollar investment into a continental missile dome remains an exercise in economic self-attrition. Traditional optics will continue to melt under the thermal load of the power levels required to kill a hypersonic vehicle, locking directed energy weapons into a permanently limited, low-power role as localized drone interceptors. By systematically investing in the chemical vapor deposition infrastructure necessary to scale, purify, and rapidly grow large-format synthetic diamond crystals, the state can finally unlock the true potential of the megawatt-class laser. The diamond shield is the physical bridge that connects the strategic necessity of the Golden Dome with the unyielding realities of thermodynamics. Mastering this material does not merely upgrade a weapon system. It structurally alters the cost of defense, neutralizing the threat of massed hypersonic aggression by turning the economics of modern warfare completely on its head. The industrial implication is that diamond becomes a strategic material, not a commodity. The state that first builds the CVD infrastructure to grow optical-grade diamond at the diameter, purity, and rate the megawatt aperture requires will field the first credible directed energy defense layer, and the others will follow on a lag measured in years or decades. This is the same pattern that decided the prior industrial races of the modern era. Aluminum smelting capacity determined who could build the aircraft that won the Second World War. Uranium enrichment capacity determined who sat at the nuclear table. Photolithography capacity still determines who leads in semiconductors. Optical-grade CVD diamond capacity will determine who commands the directed energy layer of continental defense. It is a capacity that cannot be bought, only built, and it cannot be built quickly because the growth physics are slow and the process control is brutal. The strategic return on mastering it is the inversion of the cost-exchange ratio itself. Once the directed energy layer is real, the adversary's massed hypersonic arsenal stops being a winning strategy and becomes an expensive way to deliver electricity to the defender's beam. The dome's economic promise is unlocked at exactly the moment the diamond window survives its first sustained engagement, and not one moment before. That is the material bridge, and that is why the diamond shield is not a luxury layer, but the load-bearing layer of the entire architecture. The diamond shield, the material that makes the dome real.